All right, hello, high school physics. Today we're going to talk about something that's kind of fun in this unit. We call it elevator problems. Let me click on what we're going to look at here. And you've probably all experienced this before, but if you've ever been in a big elevator and the elevator goes pretty fast, if the elevator is going down, you kind of have this feeling of in your stomach like you're falling a little bit, or when you're going upwards in an elevator that's going pretty fast, it kind of hurts your legs a little bit, and it feels a little funny. So what we're going to talk about today is really what's going on with elevators, and specifically when an elevator is accelerating up or down. So we kind of have a picture here, and really what's going on is your elevator goes up and down. We can accelerate upward, we can accelerate downward, we can even move at a constant speed with our elevators. And we're going to kind of look at all of these scenarios. And this guy right here is standing on, it looks like a bathroom scale. So, and you probably have all thought about this, hopefully, before, but when you are standing on a bathroom scale to weigh yourself, you're not actually getting your weight. You're getting what we call the apparent weight. So here's pretty much the idea is if you have a person that's standing on a bathroom scale, okay, think about what's going on. There is a force of gravity downward that that person is putting on the scale. But so that that person doesn't fall through the scale, right? There's a force back on that person. That's a normal force. So the upward force from this scale is our normal force. That's actually the reading that we're getting on a bathroom scale. Okay. And we call this the apparent weight. And so, one thing to kind of keep in mind here, the term that we're going to keep using in these problems is apparent weight. When we say apparent weight, we mean normal force. So we mean the force that the floor is putting back on you, or in this case, if you're standing on a bathroom scale, the scale pushing back up you. Basically, there's a spring inside there, and the spring is pushing back on you to keep you from falling. And so the bigger the force of gravity, the harder that that spring has to push back up on you. And again, you're getting a reading of the normal force, excuse me, when you look at a bathroom scale. Okay, now imagine, and this is kind of where we're going with this. Imagine if you were to take a bathroom scale and put it in an elevator, and we were to look at in various different scenarios what the bathroom scale would read. Now, most of the time, you're going to read your bathroom scales in pounds. We are sticking with newtons pretty much in physics. So just be aware of that. This person doesn't really weigh 750, almost 800 pounds. This just has to do with newtons. Okay. All right. So, one thing to kind of get going or to think about before we get started, I'm going to kind of show you the different scenarios of what could happen in an elevator. And let's talk about what that means in terms of the normal force and the force of gravity. Okay, so I'm going to label these as scenario 1, 2, 3, and 4. And then what I'm going to do underneath here is I'm going to actually draw the free body diagram of the person. So if you think about in the first scenario, important term here, important thought here is that the person is not accelerating. Okay, now there's some different options we would have for an elevator that's not accelerating, right? The accelerator, or sorry, the elevator could be not moving. That's not accelerating, but it could also be moving up or down at a constant speed, right? If the elevator is moving up at a constant speed or down at a constant speed, you still do not have acceleration. So here's what our free body would diagram would look like for the person. You've got a force of gravity downward. Since there's no acceleration, this upward force of normal force, those should be equal. So your normal force and the force of gravity are the same. So in this scenario, we would say that the apparent weight, right? Apparent weight is equal to the person's weight. So the force of gravity downward, because our normal force is what we're talking about here with our apparent weight. Now look at scenario 2. We're accelerating upward. Okay. In order for that to be true, we have to have a larger upward force than our downward force. So in that scenario, we would say that the normal force is greater than the force of gravity. So when you're accelerating upward, the upward force has to be bigger. So if you're looking at a bathroom scale, it's going to mislead you and it's going to make you think you weigh more than you do because of that upward acceleration. Okay, now scenario 3, this is the scenario where we're going downward, we're accelerating downward. So what does that tell us? That means the force downward, force of gravity, is greater than this upward normal force. So force of gravity is greater than normal force. So what is it going to feel like or look like? Well, it's going to feel like you have less weight than you really do. And so this is where it kind of almost feels like you're getting close to weightless, or you weigh less than you really do as you're moving downward. So that bathroom scale is going to give you a false reading and make you think, wow, I weigh a lot less than I thought. Okay. And then scenario 4. Okay, this is bad news. The cable breaks on the elevator. What happens? All we have going on here is the force of gravity downward. There is no force pushing back. And so it's going to look like on the scale that you have no normal force, that your normal force or apparent weight equals 0, because you're going to be free falling downward as the elevator falls, right? So those are your 4 scenarios. And what I want you to catch here, we're going to kind of go through a couple problems with accelerating upward, with accelerating downward, and when we're moving at a constant speed or not moving at all. So those, we're really going to focus on scenarios 1 through 3, but hey, look at scenario 4. Hopefully that'll never happen, but that's what's going on there. All right, so let me go through just 3 sample problems with you. And these, I feel like these are going to be straightforward and you shouldn't have a lot of trouble with them. And hopefully a little bit of application of kind of what we've been talking about. So here's our first problem. We're going to accelerate downwards. So let me kind of draw here. I'm going to just remind us that we're accelerating downwards, right? And here's what we know. We know that the mass of the person is 50 kilograms, and we're accelerating down at a 1.0 meter per second squared acceleration. And we're going to find this apparent weight. Remember, apparent weight is Fn. Okay, so what do? First thing we should do is think about free body diagram. If we're accelerating downward, that force of gravity is greater than that normal force, right? So when we go to write a net force equation in the y direction, which you should do, you should say, okay, my 2 forces are normal force and force of gravity. Since we are accelerating, we're going to set them equal to ma. Okay. Now we are solving for this Fn. Okay. In order to be able to kind of plug things in over here to the side, I'm going to go ahead and calculate the weight of the person. Since I know their mass is 50 kilograms, I'm going to multiply by the 9.8 meters per second squared, and I get a number. Punch this into a calculator. 50 times 9.8. I'm going to go with 2 sig figs, and I'm going to call it 490 newtons. Okay, now remember that is a downward force. So when I rewrite or kind of plug in numbers, it's normal force minus 490, because it's downward, is equal to my kilograms of 50, that's my mass, times my acceleration downward of negative 1.0. Okay, now I want to get Fn by itself. So what do I need to do? I need to add 490 to this side and add 490 to that side to get this term to go over to the other side, right? So when I punch this into a calculator, it's positive 490 minus, if you look here, 50 times negative 1.0. So minus 50, you're going to end up with 440 newtons as the normal force. Okay. Now double check, is my normal force or apparent weight less than my force of gravity? Absolutely. And that's what we want. We want the force of gravity has to be bigger than the normal force. So this is what our scale is going to read. We call it our apparent weight. Okay. All right, let me go through another problem with you. Let's go the other direction. Okay. We are going to we're going to accelerate upwards, right? So we're accelerating upwards. I'm going to kind of keep that in my brain. Let's go ahead and draw a free body diagram to show that first. Our normal force, which is upward, has to be bigger than our force of gravity downward. That's why we're accelerating upwards, right? So we write a net force equation, normal force plus force of gravity, set it equal to ma because we do have an acceleration. Now, what are we trying to find this time? We're actually trying to find the acceleration. We know the apparent weight and we know the mass of the person. Okay. Now, again, you're going to have to kind of see that if I need the force of gravity, I got to come over here and find it. Right. So since I know hey, we already did this one, 50 kilograms, 9.8. Oh, that was 490, right? On the last problem. So same weight. So we're going to plug that in. Remember, it's negative 490 because it's downward. The apparent weight is 550 because that's upward. And then we're going to set it equal to 50 times A, right? So in the next part of our equation, I'll just do the math. 550 minus 490. That gives me a net force of 60. We're going to set that equal to 50 times A. I'm going to divide both sides by 50. We're going to keep 2 sig figs, it looks like here. So 60 divided by 50. We're going to just call this 1.2, and it's meters per second squared. This is a positive acceleration because we're accelerating upward, right? All right, so this time I had to find acceleration. So we found apparent weight, we found acceleration. You probably guessed it on the next one. I'm going to make you find the mass. Okay, now, here's third scenario. Moving upwards, but what's going on with acceleration? Acceleration equals 0, even though we're going upwards, right? Because we are moving in a constant speed. Now, this problem could have very well said moving downwards at a constant speed. You can do it exactly the same way. What that tells us, because it's a constant speed, is that our force of gravity downward is equal to our normal force upward. These two are equal. Fn is equal to Fg. And that's going to help us in this problem. Write a net force equation. Fn plus Fg. This time we set it equal to 0 because no acceleration, right? Now, here's what we're trying to find. We're trying to find the mass of the person. Well, the good news is that our normal force is equal to the force of gravity. And how do you calculate force of gravity? mg. So we already know what the normal force or force of gravity is equal to. It's equal to 600. We're going to set it equal to m times, hey, 9.80. We're going to divide both sides by this 9.80. And that's actually going to give us our mass. So we're going to take 600 divided by 9.80. And our mass turns out to be 61.2 kilograms. Okay, so these are actually, I think you're going to find these to be easy and they're kind of fun to do. So there you go. There you have it. We have done some problems and you should be good to go.